Have you ever just stopped and wondered how your computer or your phone or even a search engine just gets you? It feels like magic, right? But it's not. It's actually a secret language. This whole set of fundamental rules that lets machines recognize patterns. So today, we're going to pull back the curtain and decode that language.
I mean, really think about it. You type in a password and instantly something decides if it's valid or not. You type a few words into a search bar and billions of pages get filtered down to what you wanted. It all comes down to one thing: a machine's ability to look at a sequence of symbols and say, yep, this fits the pattern, or nope, try again. Okay, let's really get into this. So to understand how machines can spot these really complex patterns, we have to start at square one. We've got to start with the absolute basics. Think of it like building with Legos. You can't build the giant spaceship until you understand what each individual little brick is for.
And it all starts with something that's actually, well, surprisingly simple. In computer science, an alphabet isn't just ABC. It can be any set of symbols we decide to work with. It could be binary, just zeros and ones. It could be letters. It could even be the basis of a DNA sequence. These are our Lego bricks, our fundamental building blocks. Okay, so once we have our alphabet, we can start making strings. And a string is just a sequence of those symbols. That's it. It's just like how a word is a sequence of letters. Now, there's a really crucial idea here: the empty string. It's a string with 0 symbols, often written with the Greek letter epsilon. Think of it like an empty folder on your computer. It definitely exists, there's just nothing inside it yet.
So, here's the absolute key takeaway. A formal language, it's not like English or Spanish. There's no grammar, no hidden meaning. It's just a collection of strings that all follow a very specific rule. The perfect example is a password checker. The language it understands is the set of all possible passwords that meet the rules, like must be 8 characters and have one special symbol.
All right, so we've got rules and we've got strings. But how do we actually check if a string follows the rules? Well, for that, we need a machine. So let's build our first one, a very, very simple pattern recognizer.
The goal here is super straightforward. Our machine is going to read a string one symbol at a time, and when it gets to the very end, it has to make a simple decision. Is this string part of our language? Yes or no. That's its entire job.
And this brings us to our very first machine, the finite automaton, or FA for short. Picture a really basic flow chart. It starts in one bubble, reads a symbol, and then follows an arrow to the next bubble. But here's its fatal flaw, the one thing you have to remember. It has absolutely 0 memory. It only knows what state it's in right now, not how it got there.
Now, these simple machines come in 2 main flavors. You've got the deterministic kind, the DFA, which is super strict. For any state and any input, there's exactly one path forward. Then you have the non-deterministic kind, the NFA, which is way more flexible. From one state, it might have multiple next steps, or maybe none at all. It can even make a move without reading anything. But here's the real shocker. Even with all those differences, they have the exact same amount of power. They both recognize the exact same class of languages, called regular languages.
Let's look at an example, because this is where it really clicks. This NFA here is built to find any binary string that ends with 0, 1. See that first state, Q0? It can just hang out there, looping on any 0 or 1 it sees. But whenever it reads a 0, it gets a choice. It can either stay in Q0, or it can guess that this might be the start of that final 0, 1 and jump over to state Q1. If it guesses right, and the very next symbol is a 1, it moves to the final state, Q2, and accepts the string. It's this ability to kind of explore multiple paths at once that makes NFAs so cool to design with.
So our finite automaton seems pretty clever, doesn't it? It can check for patterns, specific endings, all sorts of things. But what happens when we give it a problem that it just can't solve? See, every hero has a weakness, and our FA's weakness is that terrible memory.
Just think about this for a second. To solve some pretty basic problems, you need to remember stuff. What if you need to check if the number of A's at the beginning of a string is exactly the same as the number of B's at the end? Our little FA, with its handful of states and no memory, is about to run into some serious trouble.
And this is the language that breaks our machine. It's the set of all strings that have some number of A's followed by the exact same number of B's. Our finite automaton reads all the A's, but because it has no memory, by the time it gets to the B's, it's completely forgotten how many A's it saw. It's like trying to count a big stack of bills, but you're not allowed to use your fingers or write the number down. You're just going to lose track.
There's actually a really clever way to formally prove this limitation. It's all based on a pretty simple idea.
Because our machine only has a finite number of states, if we feed it a really long string, it has to visit the same state twice, eventually, and that means there's a loop. This whole insight is wrapped up in something called the pumping lemma, which basically says, hey, if a language is regular, then for any long string, there has to be a piece in the middle that you can repeat over and over. You can pump it, and the new string will still be valid.
So here's the logical trap we can set. First, we just assume, we pretend, that our language of equal A's and B's is regular. If that's true, then the pumping lemma has to apply. So we pick a string, something like AABB. The lemma guarantees there's a loop somewhere in that A section. Now we spring the trap. What happens if we pump that loop? We add more A's. We get something like AAABB. And suddenly the counts are unequal. This new string is not in our language. And that's a contradiction. It proves our first assumption was totally wrong. This language was never regular, and our simple FA just can't handle it.
So our first machine failed. It hit a wall. But we don't give up, right? We upgrade. The problem was pretty obvious. It was a lack of memory. So the solution is just as obvious. Let's give our machine a memory.
Yup, the path forward is crystal clear. We need to give our machine a way to remember things, not just one little piece of information, but a real memory system it can use to store and retrieve info to solve the problem.
And so, I want you to meet the push-down automaton, or PDA. It's basically our old friend, the finite automaton, but now it has a superpower, a stack. Now, a stack is just like a pile of plates at a buffet. You can only add a new plate to the top, and you can only take a plate from the top. This last-in, first-out system is exactly the kind of memory we've been looking for.
And just look at how elegantly this new memory system solves our counting problem. It's actually beautiful. As our machine reads the string, for every single A it sees, it pushes a little token onto the stack. One A, one token. Another A, another token. Then, when it gets to the B's, for every B it reads, it pops one token off. And what's the final check? If the stack is perfectly empty at the end of the string, we know for a fact the count's matched. Problem solved.
And just like that, with one simple upgrade, a memory stack, we've unlocked an entirely new level of power. Our push-down automaton can now recognize a much wider, more complex class of patterns known as context-free languages. And get this, these are the very kinds of languages used to define the syntax of most programming languages today.
So we've built two different machines, and we've explored two different kinds of languages. But this is really just the beginning of the story. Let's zoom out for a second and see where all these ideas fit into the grander scheme of things.
This all fits into this beautiful map of computation called the Chomsky hierarchy. You can think of it like a power ranking for languages and the machines that can understand them. See down at the bottom, at type 3? That's where we started, with our simple finite automata and the regular languages. Then we hit that wall, and we had to upgrade. That took us one level up, to type 2, our push-down automata and the context-free languages they can handle. And as you can see, the staircase keeps going up. More complex problems require even more powerful machines, climbing all the way to the legendary Turing machine at the top.
So we've seen how these really simple ideas, rules and memory, can create machines that understand language in a very formal, powerful way. And this isn't just some abstract theory. This is the foundation of how compilers parse your code, how search engines understand what you're looking for. Which, of course, leaves us with one last big question to think about. If these foundational rules of recognition built the entire digital world we live in today, what new rules and what new kinds of machines will we need to build the truly intelligent systems of tomorrow?